It was 1983, the last time I was at Simon Fraser University, talking about salmon and climate change. So I'm now talking still about climate change, but now something known as the Little Ice Age. This work is partly research and partly some societal impacts, and the research part is actually part of a PhD thesis, one of my former PhD students. So the work has actually been published, and I can give you the reference to that later. But the beginning is sort of the impacts of what's known as the Little Ice Age. That was a period starting around 1300, which followed the so-called medieval warm period, when Europe was quite warm. There was the Black Plague there and so on. And then it got colder, and various sort of environmental changes took place at that time. And there were also societal impacts. And three of these are listed here on the screen. The first one, March Across the Belts, deals with a very brief war between Sweden and Denmark. Music, I found that Karen here plays a clarinet, so I said I have a musical application or impact of the Little Ice Age. And so I'll just say that in 1962, you mentioned Adelaide, I did a degree there at Adelaide University, and I happened to hear the first time ever Stradivarius violin played by Yehudi Menuhin playing the violin concerto. So that relates to this item. Church windows is really a strange story, but I had a graduate student, a brilliant student, who came to me, and he was very interested in architecture and buildings and churches, especially in Europe, and how they might have changed from the medieval period to the Little Ice Age period. So he argues, and others, I think, support his arguments, that the Little Ice Age transition to the Little Ice Age might have had an impact on the building architecture. So now let me move these forward. So the first one, March Across the Belts. The belts are the little narrow passageways to orientate yourself. Here is Sweden, this is Denmark, this is called the Glove of Sweden. And these passageways here are known as the belts of Sweden. In 1657, the Swedes gathered here in what is now Poland, and they wanted to get this territory here, which at that time was part of Denmark. So rather than try and fight it out between Denmark and coming down this way, the Swedes came around starting in June here and working their way up, and finally at the height of winter in January, they discovered that they could cross over these passageways here because the ice was frozen over. So the impact of the Ice Age was it was cold enough that the ice was frozen over, and then they marched further, and then they were able to pass over another passageway. So there was a little belt and the big belt. And then in February of 1658, they came from behind, 12,000 Swedish soldiers came from behind to Denmark and totally surprised the Danes, and they gave up immediately. Says, okay, let's not have a fight over this. And the Treaty of Roskilde in February 1658 resulted in this territory being ceded to Sweden. So that's the military application or implication of the Little Ice Age. Next, music. So here is a Stradivarius violin. These are worth a lot of money, in case you didn't know it. There's something called the Canada Arts Council, which has a bank of very famous string instruments, mainly violins, some violas and celli, and they have a number of Stradivari. And if you want to play one of these, you have to compete for them. Okay, you can't just go and borrow one. So you enter a music competition every 3 years, and only the very top musicians are successful in winning the right to play one of these violins and to actually use it for 3 years. And so not only did I hear one of these in South Australia, but I also heard it last spring in a symphony I play in Montreal. One of the young ladies from Montreal had the right to play one of these violins, and she performed the Mendelssohn violin concerto on the Stradivari. Now, for those of you who don't know much about violins, let me just say they have a very rich sound, a very sort of almost piercing sound, a very, very rich sound. And it's been hypothesized that, well, maybe it's the lacquer, maybe it's the construction, maybe it's the magic of the play or whatever. But one hypothesis is it's the density of the wood that gives us the rich sound. The trees are fairly dense that went into the making, and the wood was chosen by Stradivari. He went to the Alps in the northern part of Italy, chose the trees himself, and let them mature for 30 years before he used them for construction. So this wood became very dense, and he used this wood to make the Stradivari. So why were these woods dense? Well, because of the Ice Age. Trees respond to temperature. If the temperature is cold, then they don't grow as quickly, the tree rings are closer together, and it gives a more denser wood. And that produces possibly the richer sound of the Stradivari violin. So, did I tell you how much one of these is worth? Any guesses? Pardon? 10 million, that's not too far off. About $4 million will buy you a Stradivari. Now, what do you do when you have one of these things? Do you sleep with it, or what do you do with it, you know? So when this young lady played it with our orchestra, as soon as she finished, she put it in her case and she strapped it to her back. And she didn't go anywhere without this violin strapped to her back. You know, you can just sort of put it down, and of course, some just walk away with it. Okay, church windows. Here's two cathedrals. Chartres is near Paris, and the Cologne is in southern Germany. And you'll see the very different type of stained glass. So this is sort of at the end of the medieval warm period, and the glass was quite dark, very rich in color. And but 100 years later, which was the start of the Little Ice Age, the glass they used, not too far away, Cologne is not that far away, the glass suddenly was clear, called grisaille. Why? Why the difference? Well, the hypothesis is that during the medieval warm period, the skies were very bright and sunny, so they had to darken the windows so the churches would provide a nice ambience and not be too bright inside. But by the time the medieval warm period came, it was very rainy, cloudy conditions, and somehow the church builders and the ecclesiastical community decided we still want some light in there, but the only way we're going to get enough light is to have more clear windows. So I asked for a globe as a little demonstration here. So why would things change? Well, there's something called the North Atlantic Oscillation. Does everyone know what the North Atlantic Oscillation is? Who does not know what the NAO is? Okay, there's a couple. Well, the NAO is a oscillation, change in the pressure difference between a big low pressure system which sits here over North Atlantic and a high pressure system which sits over the tropical, over the Azores. So if you take the pressure difference, normally if you have a very deep low and a high pressure, then the NAO index, the pressure difference, is positive. So when you have a very deep low here, what happens, and I better get this out of the way, there we go. What happens is that with a very deep low, the storm tracks tend to pass over Scotland and over Norway here. So all the stormy conditions go that way, and therefore it is quite pleasant and sunny around Paris where these churches are. But when the Little Ice Age started, it is believed that the NAO index changed sign whereby this became relatively high pressure, a weak pressure, and the upshot was that the storm tracks went across Europe rather than to the north. And if the storm tracks go across, then they would bring rainy, cloudy conditions to this part of the country. So the North Atlantic Oscillation will also play a part in my talk, as you'll see later. So the NAO is sort of like, in a way, El Nino of the Pacific. The NAO oscillates on timescales of years to maybe decade and maybe even longer. And so it's a natural climatic phenomenon, just like the El Nino Southern Oscillation is in the Pacific. So Christopher Simmons, by the way, is a former student, a master's student. He's now actually a PhD student working on a totally different climate application. But he was the one who actually went to these churches of Europe, and he measured the light through these different windows, both under sunny conditions and cloudy conditions. And so we actually have a paper published in the Architectural Science Review describing the physics of the light transmission. And we have another paper coming out in Atmosphere Ocean trying to link the climate change to the change in the church windows. As I said earlier, this talk is based on the research of Jan Sedlacek. He is a Swiss from Zurich area. His father came from Prague, so it's a Czech name, but he married, his mother was from the Engadine Valley in Switzerland, of Romansh descent. So this is sort of the more technical title, if you like, of my talk, called the transient simulation. Simply mean looking at how the climate changed through time during the Little Ice Age, and also what happened as we left the Little Ice Age. And today, of course, we've left the Ice Age behind, and the bottom line is it's really we left the Ice Age because of greenhouse gas production, producing more greenhouse gases. But the question is what caused the Little Ice Age? That has been open to debate, and I try to explain to you what I think was the main reason for the Little Ice Age. And then I'm going to be working, showing you simulations of a model of reduced complexity. These are also known as Earth system models of intermediate complexity. And there have been many groups around the world, mainly in Europe, but a few in Canada and the US who have developed these models. And this particular model that I'll be using, in fact, was developed by one of my former graduate students, Andrew Weaver, who's a professor at University of Victoria. So I have academically a son who developed a model, and now the father is using a model developed by the son. And there's a granddaughter of mine in the room here who works also very much with this model. Do you know who that is? Kristen, yes. Wave your hand, Kristen. Okay. So, and I also have great-grandchildren and even great-grandchildren now. So I've been around a long time. Pardon? There's one. There's a great-grandchild. There you go. There you go. Okay. I guess I better stay on this side. So, little climate perspective. The Holocene is the last 11,000 years, roughly. But there was a warm period about 6,000 to 7,000 years ago. And then following this warm period, there were sort of several glacial advances, and these were called by this guy the Little Ice Ages. But today, this collection of glacial advances is known as neoglaciation, and that ended in the Little Ice Age when we had the biggest glacial advance. And that's when you see pictures of Switzerland with the glaciers, you know, right down to the bottom of the valleys and so on. And then around 1850, the Ice Age started to disappear. And for the purpose of this talk, I will call this last 150 years the industrial era. So the Little Ice Age was before the industrial activity, and it actually started earlier. So in reality, we should have started this study around 1300, 1200, but we had to provide some data input to drive our climate model, and we didn't have any data before 1500. So that's why the model study started at 1500, when we were truly into the Ice Age. Any questions, by the way? I know you like to have questions, but I sort of give you some background introduction. Do you have any questions at this stage? I believe there's some students here who are taking some notes, so they might be asked something a little bit later. Yes, you're not a student, are you? Go ahead.
Eternal student.
Yes.
Why do you say that we came out of the Little Ice Age because of greenhouse gases?
Because I'll show it from a model result. I'll force a model with 3 different types of radiative forcings, and when you put everything together, you can see the warming, which coincides with the increase in greenhouse gases. So it's a model result. So if you believe in models and physics, that is why. Okay, so some motivation. I mean, people were aware. So by the way, this study was done in connection with the interest of many of us at the time in the Arctic and the sea ice changes in the Arctic. And so I guess the idea was to look at the Little Ice Age and just to see what were the conditions in the high latitudes, especially the Arctic. No one had really done that before. Everyone was looking at lower latitudes. And so part of the reason for this work is to see what might have happened in the Arctic during the last 400 or 500 years. So this shows you an atlas projection where they obviously didn't know the geometry very well, but they seemed to be under the impression that there was a lot of ice at the time. And then just a few years later, it must have really been socked in, because obviously very few ships went in there at all. They did define Greenland quite well and the Labrador Sea, Baffin Bay. So 1692 was clearly a well-established part of the Little Ice Age. And then even up to 1870, still there was some ice there, but now you can see that the definition of the geography was much better. So clearly we were sort of on the way out of the Ice Age according to these maps. So Some of you being geographers, I thought you'd appreciate these atlases. Too fast. So looking at now recent history, we're well aware that 2007 was a drastic year for reduction in sea ice cover. Here is sort of the climatological picture during the month of September. Yeah, September is sort of the minimum month. That's like the end of the summer, but that's when we have the least sea ice. So this is the climatological picture over the satellite record. And in 2007, we had this minimal year. Before 2005 was quite a bit of reduction. And I believe in 2011, we also were in a very reduced state, almost as little ice as was shown here. So we know that the ice is certainly going down. So naturally, reversing the question, well, was there more ice during this cold, the Ice Age period? IPCC, Intergovernmental Panel on Climate Change, has done many runs into the future for the next 100 years to see whether the sea ice, is expected to go down. March is sort of the peak winter. September is the peak summer. These are the observations from satellites of the sea ice cover. And you can see that the models actually tend to not predict that well the observed reduction. So here, in fact, the models really predict a much slower decrease in the sea ice. So it's been predicted that by 2100 and maybe even before, during the summer, the Arctic will be completely ice-free. So that's the future. And even now at 210, which is somewhere around here, people believe that we are in a new normal for the Arctic sea ice conditions, i.e. the ice is thinner, there's much less cover, and also there's much less multi-year ice. The ice that sort of is normally piled up for years and years north of Greenland and northern archipelago, now that ice is quite mushy and it does not very much last from year to year. So we now speak of a new normal for the Arctic conditions. So we're already sort of entering a new period. Okay, so this is from, what was that year there? From 1900 to 2100. So the question is, okay, what about going back? No one's ever really modeled the previous 100 or 500 years, and that was what the purpose of this PhD thesis was. Was there more ice? Was it thicker? And so on. Okay, I have to be very sensitive. Okay, so the motivation then for the work was the realization that sea ice responds both to mechanical forcing, the wind, driving, pushing the ice around, piling the ice up, and also to radiative forcing, just heating, temperature heating, due to solar heating, due to greenhouse gases, and so on. So one of the ideas was to tease out, what is the role of the different forcing mechanism? Is it a combination? Does one affect one and one affect the other, and so on? The ocean heat content is a very important factor, certainly important for climate, because the oceans are great stores of heat. All the heat in the atmosphere you can store in 3 meters of ocean water. It's a very good reservoir for heat. Have there been changes in global hydrology, the salinity, temperature of the ocean? And a very famous circulation is the so-called meridional overturning, which is largely a buoyancy-driven circulation where you have sinking of water in the North Atlantic, that water slowly going down through the Atlantic Ocean into the Pacific, Indian and Pacific Oceans, and then returning as warm water 500 to 1,000 years later. And there have been a lot of studies which show that if you export a lot of sea ice out of the Arctic through Fram Strait, that sea ice being very fresh provides a buoyancy cap on top of the surface waters there. And with that buoyancy, that prevents the North Atlantic water from sinking down, because what happens in the MOC is the warm water comes north, it loses heat, but it's quite salty water, and then it sinks. But if you suddenly flood the North Atlantic with fresh water from sea ice, then you add such a stabilizing buoyancy layer that you prevent that sinking. These are called hosing experiments that models do. We hose the water and see if we can stop the sinking. So these are the sort of questions that climate people and atmosphere ocean people want to look at, and certainly sort of questions that also impact on biological, biogeochemical cycles, which I won't talk about, but that is the expertise of Kirsten, certainly. Okay, so here's the outline of my talk. So you've already had the motivation, and now a little bit on the description of the model. So any questions to this point? No? Yes, Kirsten.
Yeah, on the church windows again.
Yes, right.
I think it's sort of what you said makes sense if the little ice age was cloudier.
Yes,
than,
yes.
than the previous period. Is there any evidence for that? Do we know that?
That's one of the challenging things, to try and find evidence. There is some evidence, and Chris Simmons and I have a paper coming out in Atmosphere Ocean next year which points to that evidence, but it's very indirect evidence. It's looking at bogs, in fact, certain types of biological indicators which are sensitive to humidity, for example. So those are more frequent during the Ice Age. Also, people have looked at shooting stars, for example, and suddenly the density of sightings of shooting stars is much less, indicating cloudier conditions.
There is some evidence with the famine record.
Also the famine record of rain. Okay, right. Yes?
I didn't get the point on church windows.
Yes?
It was that the more transparent church windows were at the time when they needed more light.
That's right, yeah. And that's when it was cloudy and overcast and rainy. Okay? So in other words, when you're in church, you sort of like a certain light. You don't want too much light and you don't want to be too dark. So when it's very sunny, they put in the dark glass to tone down the light inside. But once it was rainy and cloudy, it was too depressing to be in those dark churches, so they put in the thinner glass. That's basically it, yeah. Okay, so next I'll describe the model. So this is a rather early version of the Uvic model. And then one of the challenges was that the model itself needs to provide fields, forcing fields for the winds. You have to specify the winds in the model. And we've only been making wind observations or putting together records for 50 to 100 years. So what do you do before observed wind patterns? So we had to do something creative in that regard. And then the external radiative forcings are of three types that I will look at, and there are others which we neglected. But the forcing of greenhouse gases I talked about, but also there's volcanoes. That's the big one. Volcanoes, when they erupt, they produce little particles in the atmosphere. They block out the sunlight, these aerosols, and that can produce a cooling. So we know from recent volcanic activity, El Chacon and so on, that the temperature does drop by a degree or two. Not for a long time, but it does drop for a year or two, and then it sort of bounces back up. So it turns out that during the Ice Age, and I'm giving this story away, during the Ice Age there was a lot of volcanic activity. A lot of volcanic activity. And the third thing, is the solar constant. So the solar constant is not constant. So the actual amount of energy being released by the sun does vary a little bit. And a lot of people have argued that it's the solar constant. Even maybe the solar constant is changing enough to be as important as greenhouse gas rises. So those are the radiative forcings we're going to examine. And then the results are, well, the first thing is just to look at the annual surface temperature, and that we can compare against the paleo records, the sort of things that Karen here is an expert in. And so people have put together 500,000-year records of air temperature, mainly for the northern hemisphere, and we put these all in one graph, and then we plot what our air temperature does in the model and show that it more or less follows what's been observed. And then, as I said, I was interested in the sea ice. I've worked in sea ice a long time, and also in the ocean conditions. So the Earth system climate model of the University of Victoria, an early description of the model is published in 2001. That's version 2.6. And what are you up to now? Version 2.10 or 11 or something?
Close to 3.0.
3.0, okay, so you've gone through all the digits and you're up to 3 now. Okay, very good. So what we're dealing with is basically a physical climate model, and what has been added more recently is a lot of the biogeochemistry, chemistry, sediments, I think, and ice sheet. We've got a coupled ice sheet yet. That's also in there. So it's a much more sophisticated model than we used. The resolution, in other words, how big are the grid cells, 3.6 degrees zonally in the east-west direction, and meridionally 1.8 degrees. So it's quite a coarse climate model. But because it's quite coarse, you can do long-term simulations. The ocean is quite sophisticated, a 3D ocean model. But the atmosphere is very simplified. It's EM stands for energy-moisture balance. So it's basically a thermodynamic, one-layer thermodynamic model for the atmosphere. And so there's no dynamics in the atmosphere. We do not have storms and highs and lows. So therefore, we have to prescribe the winds in the atmospheric part of the model. The sea ice is both thermodynamic and dynamic. Thermodynamic is a two-category model, technical terms. You either have ice or open water. The dynamic model is actually a model that one of my former students, Bruno Tremblay, developed. So we actually put it into this Uvic model. Normally, they run with a slightly different sea ice model. So we worked with what was called a granular sea ice model. So the question is then, what wind stress fields do we use? Because there are no observations which go back 500 years. And how important is wind forcing for the variability? Is it really different between the Little Ice Age and the modern, or does it just produce, the net effect of storms is just to produce sort of lots of natural variability and maybe nothing to do with the Little Ice Age? So the four approaches that I mentioned here, ANAW stands for analog winter, and I'll explain what I mean by analog, but we took some paleoclimate studies looking at the North Atlantic Oscillations, which were done in Switzerland by Lutherbach. And we used that paleo record to try and generate some wind fields by doing some translation of modern fields to back in time using the NAO index. That's winter. This is monthly. Decomp is another sort of statistical technique we use. And ECAM stands for an atmospheric model from Germany, Hamburg. So just taking some winds that have been used in a climate model run there. Now this is kind of technical stuff, so I won't go into too much detail, but it's kind of fun just to show you how we modelers work. We have to be very imaginative because if you don't have the data, you're sort of paralyzed, so you have to generate data that you might need to force a model, and that's what we did. So here is the North Atlantic Oscillation, and this is the so-called North Atlantic Oscillation Index for winter. So that index is simply the pressure difference between the Azores high and the Icelandic low. So when that is positive, as it was here the last few years, large and positive, that means the storm tracks went way up to Norway, and you had a very deep low. When the index is negative, as here around the 1970s or so, that means the low was very weakened, the high was also much weaker, and the index actually changed sign. And in that case, the storm tracks would go across Europe. And in fact, we did a study once whereby we were able to actually correlate the NAO index with rainfall over the Ural Mountains in Russia, and it did correlate very strongly with this NAO index. So again, a high period, fairly high for quite a while. Now, as a theoretician, you have to be very imaginative, but also very optimistic. And I would say, and I hope you'll agree, that it looked like it was more negative values here than there are here. Would you agree with that? Just sort of eyeballing that time series. There's lots of variability, but the positives aren't as big as they are here, and certainly there seem to be a lot more negatives. Well, that's stretching a bit, but that's sort of the evidence that maybe there is more of a negative phase for the NAO during the Little Ice Age period. Now, people have gone back, and so we'd have to argue then, therefore, the NAO is more positive in the 1200s to produce the arguments that I did, or to substantiate the arguments I did. Okay, so what do we know? We know that from real data, from Boulder, NCAR, National Center for Atmospheric Research, and NCEP, which stands for what, Kirsten? National Center Environmental Protection or Prediction or something. Anyway, that's a big weather center, fancy word for the weather center in Washington, D.C. So they put together so-called real analysis data. They constructed this NAO index for this period. So this is sort of quite reliable, really from the observations of the wind stress. But what we want are the winds way back here. So what we have to do is say, look at the year 1605. Suppose we want the winds for the year 1605. Well, we know that the winter index during this year was 0.55. So what we did, and this is Jan Sedlacek's idea, and he got a PhD out of it, so I guess it wasn't a bad idea. he said, let's move forward, sweep through the observed record until we find 0.55. And in 1972, 0.56. That's close enough. So what we simply then did was cut and paste the winds from the present, which we have real observations. We simply pasted these winds back to the year 1605. So he went through the whole record here for each NAO value, and he says, okay, we find a value, and we just take the winds for the present and use them back then, some time ago. Okay, so the ANA monthly is the same sort of thing, except we use monthly resolution when we had it more recently, and rather than winter. So that's a similar approach. Then the decomp method was, again, going to a particular grid cell. We want winds for a certain place, so we compute them. We plot the winds, and then from the winds, we compute a mean value. We can compute an annual climatology. Then we can compute anomalies, both monthly and seasonal, so this is a deviation from the mean. Then we would take these anomalies and regress them onto the NAO index for the recent period, 1950 to 1999. So this regression is a statistical technique which produces a spatial pattern of what's happening over the ocean. And this field shows a large NAO signal around the North Atlantic. And other areas of the globe, the NAO signal is quite weak. So then we defined a remainder field between the observed winds, which were this field here. We subtract the mean, and we add this regressed field, and that produces a deviation, if you like, from what's really there and what we've computed. So then we construct it as our forcing field. So this is the decomp field, is the mean plus this regress spatial variability pattern multiplied by the NAO index, where now the NAO index is calculated from this paper for all the years, and then we scramble up some remainder wind stress fields to provide a little bit of noise to the system. Okay, finally the ECAM approach simply uses monthly winds taken from another climate model which has a sophisticated atmosphere, ECAM 4, and that was winds which came out of an atmosphere coupled to an ocean, and these winds were provided by this colleague Zorita. Okay, coming back to the radiative forcings, I said that what we used were the same as actually used by Crowley, and also that came out of this model. Okay. So what are these external forcings? I already mentioned there's the aerosols. So this provides a cooling, a lot of volcanic activity, blocks out the sunlight, and produces a cooling. And you can see that during the period starting around 1600 and before, that there was a lot of volcanic activity, and these A, B, C, D, and so on marked particularly strong volcanoes. Also even in 1800. And then maybe there's still some volcanic activity, but now you see this red curve is the observed rise in greenhouse gases. And very little volcanic activity here, a little bit here. These are some of the events we know in El Chacon and so on. The insolation, this is a so-called solar constant. So this shows you, yes, there was a little bit less heat coming from the sun, a bit more, and then perhaps a slight rise, but nothing in terms of radiative forcing. So this is the radiative forcing, the amount of energy, the watts per meter square, the energy flux per unit area. So the greenhouse gases are providing of the order of 2 watts. Individual volcanic activities are much more than 2. They are 4 and even up to almost 6. So while the volcanoes are short-lived, they have a very strong radiative forcing, and therefore it's not impossible they could provide a cooling, for several years. And then if you have another volcanic activity, you've barely come out of a cold patch and you have another big blast of stuff coming out of a volcano. There are other important things that we could have looked at. For example, the effects of deforestation. If you clear the land, then of course you're changing the albedo of the planet. The sunlight will be reflected off, so it provides a cooling effect, whereas a forest is dark and it absorbs heat. So if you have land clearing, that has a big effect. Also, other vegetation changes, just the type of cover you have could also affect the albedo. Okay, so we've got these 3 forcings. And we've got these 4 wind fields. So here's where the fun becomes as a modeler, a theoretician. What do you actually run? How do you run your model? Well, I showed you these 4 wind fields, and there's these 3 radiative forcings. So we can combine all the radiative forcings together, and we call that the VOLSOG. Okay, the VOLSOG standing for volcano, solar, greenhouse gas changes. So that's VOLSOG forcing. Or we can say, look at one of these radiative forcings alone. We could say keep the greenhouse gases constant at 280, the pre-industrial value. We could keep the sun constant, but we could only look at the effect of volcanoes. So that would be our vol forcing, okay? And we can have GHG forcing, UG forcing, that's only greenhouse gases, solar constant, no volcanoes. And then finally, we could just vary the solar and keep the others constant. So we've got these, and then we could also have everything constant, radiative forcing constant. No change in greenhouse gases, no volcanoes, constant sun. So the only thing changing then would be the winds. And we call that sort of if you like, a control run. Okay, so we can put everything together, we can do one at a time, and we can have nothing, just winds. So there's 5 sort of types of forcings, and then we've got 5 different wind fields. So you multiply those together, and you've got 20 combinations we can do. Now, do you think I'm going to show all 20 runs? No, I'll save you that. But I'll sort of show you a summary of some of the results, and just say that really it didn't make too much difference which winds we used. Okay, let's get back to reality. So all these curves here, the colored curves, are from various paleoclimatologists, Jones, Mann, Biffra, Esper, Wang, and Moberg. You would know all these people. So this is their reconstruction of the temperature records, before the observed record, using things like tree rings as a measure of temperature, looking at bore hole temperatures, looking at coral records, and so on. And while there's certainly a spread, you can definitely see that there was a cooling which started, well, maybe it didn't start till 1400, maybe it started earlier, but you can definitely see there were some cooling trends in the 1300s, and certainly by 1500, things were really dropping off in some of the records. Moberg argues, and I met Moberg in Sweden when I was on sabbatical there some years ago, and he figures his is the best record of all. And I like it too because it agrees best with our data. Okay, so the black line is the model result for the analog winter. This is the black line for analog monthly. This is the decomp, and this is the ecam. And you can see all our different wind fields produced cold conditions. When was the battle between Sweden? It was there was 1700, so it was around here. So there was the cold period. Indeed, it was bloody cold at that time. Okay, so we've simulated that. Stradivari, he lived around 1700, before 1700 to 1800. So indeed, during his period, the trees were slow to grow. And as I said, he cut his trees down 30 years, so they were certainly growing during the very, very cold period. You can see that we do deviate in the present. Our model produces too much warming, and that's as largely because we did not include aerosols, sulfate aerosols, because they sort of tend to dampen the greenhouse gas warming. Okay, so this is the temperature anomaly. These are the annual anomalies for the different winds with all the radiative forcings thrown in, with the solar variability, with the volcanoes, and with the greenhouse gas changes. Yeah, question.
You just said confused me a bit because I thought the VOLSOG run did include volcanoes, but didn't.
No, VOLSOG is everything: volcano changes,
Oh, yeah.
Solar constant changes, and greenhouse gas changes.
Right, but you just said that you did not include the aerosols, but I thought the aerosols,
Oh, that's right.
Came out.
I did not include the sulfate aerosols, the modern aerosols. So I have aerosols from the volcanoes, but not the aerosols from modern industrial pollution. That's what I meant to say. Yeah. Right. So in other words, the last 50 years, we've put a lot of stuff in the atmosphere, and that is not in the model. Okay. Thank you. If we had, that would have brought down the change probably about 30% and would have been right on the data. Okay, sea ice. So I said I was interested in sea ice. Was there more sea ice either by area or volume? And if you look at the area, you can see that during the ice age up to about 1800 or 1750, the average was around 15, And during the sort of more recent era, the average was maybe close to 1,400. So before greenhouse gases and global warming was talked about, we talked about an average winter. No, this is annual, so an average annual value of around 14, and before is about 15. So roughly 10% more sea ice in terms of area. And these are all the different model results, again, with all the thermodynamic forcing and the different four winds. Same for sea ice volume, a little more spread in the data for volume, but also I would say we'd argue that there is less volume than there was in the Little Ice. So there's more volume during the Little Ice Age. So colder conditions, more sea ice, both in area and volume. That's the bottom line. So now suppose we do the so-called control simulation, whereby we fix all the radiative forcings. And now we're just looking at the anomalies. And what you see here is indeed a lot of variability, quite large fluctuations, both in area and in volume, but more so in the area. And so the winds, of course, do push the ice around a lot. And you can see that these variability, these peaks, obviously there's a lot of variability. There's just sort of a few years. But you might describe this variability as sort of decadal or maybe multi-decadal variability. So the winds that we generated from our methods produced sort of decadal and longer decadal scale variability in the sea ice area and volume. Okay, so I still want to answer the question, though, but how important is the radiative forcing in terms of these larger ice conditions during the Ice Age? So then what we did is we subtracted out what the winds do in the model and only look at what the thermodynamic forcing do. So we simply took our runs and subtracted out the component due to the winds, and what you see here is therefore the net effect of radiative forcing. So the different radiative force runs minus a control, and what you see here are four cases. The Volsag is everything minus control, volcano minus control, solar minus control, greenhouse gases. And A, B, C, D are these big volcanic activities. And now look at, just for example, E here. You see that the black and the purple coincide. You also see that the black and purple coincide back here. So what this tells you is that in terms of radiative forcing, it's really the volcanoes which is the most important forcing. Because the difference between everything and volcano only is very little in many of these cases. And it's even more evident in the sea ice volume. Look at the nice correspondence between the black and the purple curves. However, once we get out of the Little Ice Age, after 1850, now you see that the black and the red coincide. So it's the greenhouse gases which are the main dominant forcer. And yes, the solar forcing has a little bit of effect there, but it's not as important as the greenhouse gases in producing less and less. The greenhouse gases were going up. The solar forcing was going up a bit, but not nearly as much as the greenhouse gases. So thermodynamically, the Little Ice Age, certainly in terms of the sea ice, it was the volcanoes that were extremely important. Southern Hemisphere. Maybe this is only of interest to the penguins, but nevertheless, what about the Southern Hemisphere? The Arctic is very different from the Antarctic because the Arctic Ocean is enclosed by land, and so it's harder for the ice to sort of move around and escape. And also, it's you're right at the pole, so it tends to be thicker. In Antarctica, you've got a big continent over the South Pole, and the ice is sort of out the outside, and it's allowed to sort of expand and decrease and move away. The upshot is that the ice is much thinner in the Arctic. Its average thickness is a meter or less. And because there's no boundary constraints, when the winds get blowing, they can push the ice around a lot more. So what you see here is a lot of variability. And also you can see the winds are obviously very important, produces variability, but you do not see much in the way of a big change between the Little Ice Age and the present. And if anything, maybe it looks like there's actually an increase in the sea ice cover in the last 50 years. Sea ice volume, again, a lot of variability, but no clear trends. So the Antarctic, is not responding the same way as the Arctic. Again, if you look at the control simulations, a lot of variability, just as we did before. And if we subtract the two, it's kind of a mess. So life is not so simple because now This is taking out the wind effect. And you can see that a lot of these curves are sort of piled on top of each other, the black, the purple, the red. In a few cases, the purple and the black coincide, showing volcanic activity is important. But in terms of volume, it's very hard to separate out. The only thing that's fairly clear is that towards the end, the black and the red coincide, as it did in the case of the northern hemisphere. But during the Ice Age, it's a much more complex picture. And it's kind of hard to interpret, exactly what was happening in the southern hemisphere. Okay, getting to some summaries now. Before I discuss oceanographic changes, what happened to the ocean temperature, heat, and so on. So the northern hemisphere surface air temperature, the annual values agree quite well with our observations. The cooling around 1800 is more pronounced than the reconstructions, and the warming is definitely too much in our model because of the aerosols, the sulfate aerosols. In terms of sea ice, we had more sea ice in volume during the Ice Age. Wind-driven fluctuations account for about 10% of this total area changes. Thermodynamic functions are comparable to the thermodynamic dynamic, and volcanic activity is a main radiative forcing, and greenhouse gases come later. For the southern hemisphere, I argue that there were no really strong trends. The wind-driven fluctuations tend to be quite large, again, because the sea ice is much thinner during in the southern hemisphere. Thermodynamic fluctuations are about half the magnitude of the wind fluctuations. I didn't show that in great detail. Before 1800, all the radiative forcings are involved in the sea ice changes. In the 19th century, volcanic forcing could have been important. And finally, in the 20th century, also the greenhouse gas changes and insolation changes could be responsible for some of the downward trend. Okay, let me now go to the ocean, and this will be sort of my last little topic. The ocean heat content is basically the temperature of the ocean averaged over the depth of the ocean. And in an earlier study by Crowley, 203, using the same forcings, but using an ocean without winds at all, no ocean circulation, he found that there indeed was a loss of heat content during the Little Ice Age, starting from the medieval warm period, and then the ocean warmed. So this trend here corresponds to this run here, this orange curve. This would be the closest analog. So we indeed have a trend, but when we put in the winds, as these other curves represent, the winds, you see, do not allow us such a rapid cooling as was found earlier. So the winds are actually important to reduce or temper the cooling trend. For the upper 300 meters, not studied by this guy, for the upper 300 meters, we see that the ocean was indeed cooler and is warmer, and this little black line here agrees with the observations of Levitus, from Levitus. The black line indicates that our heat content is very well reproduced in the model from compared to what is observed. Now this is one of my more fascinating pictures. This shows you a time series from 1500 to 1200 from minus 90 to plus 90, 90 south to plus 90. And here is what the wind is doing. And what you see here is not much. This yellow indicates perhaps slightly sort of warmer, a bit cooler here, a bit warmer. But what you definitely see are these bands here about every 50 years. And these bands have an angle planted up, whereas in the lower latitudes between 60 and minus 60, these bands are sort of up and down. So what this indicates is that the winds are producing warm events penetrating into the Arctic Ocean about every 50 years. And we've observed this in the last 50 years to 100 years. People have observed one or two of these warm events going into the Arctic. And we have simulated this with our model with the wind forcing. When you put in all the volcanic, solar, and greenhouse gases, now we really see the cooling part of the ocean, upper 300 meters, and then the warming of the ocean. But still, this picture is not that much different from that. So thermodynamics is very important at the middle to high latitudes, but at the extreme high latitudes, the winds are extremely important in producing these advective warm events into the Arctic. You can see similar things in the southern region, but they're not nearly as clear-cut. but you do see this multi-decadal variability. Okay, now let's look at the temperature of the ocean, the difference between the Little Ice Age and the industrial. So this, in fact, is industrial minus the Little Ice Age, and yellow indicates that the industrial ocean is warmer. So all this yellow indicates a warmer ocean. This is with everything, with the winds and all the thermodynamic forcing. When you take out the winds, you can see that we do not get this penetration of warm water. So the winds are very important for getting sinking in the very high latitudes. And so we do not get sinking, only go to 1,000 meters instead of right down at the bottom of the ocean with the winds. So the winds are very important in helping to overturn and get heat down to the bottom of the ocean. In terms of salinity, looking at the difference, not a lot of change. This shows that industrial minus the cold period indicates that there are saltier events coming into the high latitudes, and this little blue patch indicates a salinity difference, which is due to more ice being formed and more salt rejected as ice is formed during the Little Ice Age. If you put the two together for density, density sort of looks very much like the temperature. So you have denser, this blue color, and the difference is in terms that we had definitely denser water during the Little Ice Age. Okay, lastly, my last little picture cartoon here is the overturning. So here's the North Atlantic, sinking water coming up, and then there's Antarctic bottom water being formed. So since the Ice Age, we have about 16 Sverdrups units of discharge coming down to the ocean and some overturning here. And Broker proposed that the overturning was weaker in the north and much stronger in the south. Our model results confirm a little bit. We did find that our AMOC, our Atlantic mineral overturning, was reduced depending on which wind field we used, and the ventilation was enhanced, but we got nothing like what was proposed by Broker. And maybe the simulated changes, the difference between the Little Ice Age and now is probably due to more to the winds, due to other factors which Broker proposed. He was bringing in various biogeochemical effects. Okay, I have pretty well finished everything I want to say in terms of new results. So this is a summary of the ocean changes. So the ocean dynamics reduces the downward trend in heat content that was found earlier by Crowley. Between 60 north and south, radiative forcing is very important, shows the warming. But in the polar region, we have these so-called episodic warming events penetrating the Arctic every 50 years. And that's consistent with one or two events that actually have been observed. Temperature changes in the top 100 meters, 600 meters are caused by radiative forcing, but temperature changes deep down, you do need the winds. Salinity changes are generally small except in the Arctic, and density changes are a composite of temperature and salinity. And the MOC, hypothesized by Broker, these changes we show are really due to atmospheric forcing rather than changes in radiative forcings. So overall summary, I've shown that we're able to construct 4 different wind fields, and really the results didn't show that much variation between them. If they showed any results, maybe the ice volume tended to respond differently. We combined these with the different radiative forcings, and we showed that in terms of annual temperature, Northern Hemisphere, our model doesn't do too badly. So we have more sea ice, more volume during the Ice Age. We had, in the Southern Hemisphere, maybe not much difference. Ocean heat content shows that the ocean definitely has warmed up. And then we had these advective changes into the high latitudes. And the changes in the MOC are mainly wind driven. And I do believe that is my last slide. Yes, so I conclude there. Thank you very much.
If time for questions, thank you.
Okay, good.
Yes.
You mentioned that you're leaving out industrial modern aerosols.
That's right, yeah.
Why are you leaving them out?
I guess we didn't have the forcing fields in the same format that were obtained from the earlier models that were used by Crowley and by the German group. So I think just to not introduce as many changes as in the mean, so we could compare results with previous results and have some similarity. Since we know the effect of these aerosols, modern aerosols, we could have added them, but we didn't, and we know that they would have produced a little bit more cooling in the last 30, 40 years.
But according to IPCC, that's one of the large uncertainty areas.
The amount of cooling due to, I'm not so sure. I think we believe it's roughly 30% cooling that they produce. I don't think they're going to be as large an effect as the greenhouse gases themselves. I think that's pretty well agreed.
No, but have you ever tried to cook them in?
No, I've not. To answer your question. The professor is supposed to answer a question simply, right? I still haven't learned that after 45 years. Question.
Yeah, so can you say anything about the time scale, maybe since the 1600s, for the coastal ocean's productivity off the east coast of Canada? Because there have been these long records that have been reconstructed for North Atlantic cod. That maybe there's something there about the dynamics of cod.
Okay. Well, the model resolution doesn't really resolve, the coastal area, but in terms of the overturning, if the overturning atoll, and that includes like the Labrador Sea overturning, then there could be certainly changes that might be on these sort of multi-decadal time scales. Because I showed that around 60 degrees north, maybe starting at 55, there were these long changes associated with wind-driven changes. In terms of thermodynamic changes, the temperature changes are very small, so they may not be as important as the wind effects, which would be for overturning and bringing up nutrients and so on. But certainly that multi-decadal variability was there over the period and might be related. So you could actually, this work was published in 2 papers in Climate Dynamics by Sedlacek and myself. It was either 209 or 210, and so you could actually pin down those events where the advective events were going in when you had strong wind events. Maybe you could try and correlate those with some biological or productivity records.
Okay.
A suggestion.
Karen?
Karen, sorry, yes.
The reconstruction of your wind fields is
Yes.
going to depend strongly on your faith in your NAO index.
That is correct.
1600.
Yeah.
Can you comment on how that was reconstructed for that time period and what uncertainties would be?
I can't, because it was done using historical records of pressure you needed. So the Lutebacher looked at pressure records, estimates of pressure. How he did it, I'm not sure, because what sort of records they have. Barometer, I guess, effects. So it was a historical reconstruction that was done. And so you have to accept what he did was a fairly good. I think there are other estimates of the NAO that people have done, and they showed he's produced a pretty good record. Okay? Question.
I think modelers are still pretty well downplaying solar effects as being significant, small but not overly significant. I think there's still some debate about certainly the main solar minima periods, the monitor, spore, and so forth. When I think I was looking at your graphs to see some of your cold excursions occurred during those time periods.
Yeah. They're certainly important, but they're not that important, let's put it that way. They could be looked at more closely, but I think recently the way the solar variability has been going, it's actually been counter to the greenhouse gas warming effect. So it's certainly an important factor, and there are people who argue that not only solar variability, but also dust from the solar clouds, can affect moisture, can affect cloud production and so on. So that's another effect that people are. Solar wind effect, yes, exactly, yeah. But we didn't study that at all, yeah. Okay, another question at the front here, yes?
I noticed you said the cells were 1.8 degrees north-south.
And 3.6 east-west, yeah.
Is this a purely advective model? Because you should have a vertical.
Oh yeah, no, we do have 19 layers in the vertical. So we have vertical resolution of 19 layers, which with more resolution in the upper part of the ocean than the deep ocean.
No, in the atmosphere.
Oh no, the atmosphere is only a 1-layer atmosphere. So there's no dynamics in the atmosphere. So everything is, yes, in fact, it's diffusive except for the moisture, I think, is advected, yeah. So it's a purely diffusive atmosphere. So there's no winds. So the only thing the winds are doing is pushing the ocean around. Okay, any other questions? Yes.
So you show that in this model, the the changes in the meridional overturning circulation you see are mostly wind-driven. So I wonder what forcings or what mechanisms do brokers suggest? And
it's kind of weird. I tried to understand this paper and I couldn't, quite frankly. I mean, Broca's a brilliant guy, but it was not clear what he was driving at. He somehow was bringing in radiative forcings as being important. Well, I guess affecting the buoyancy somehow. But it was not clear to me what he was actually driving at.
So you find a denser surface ocean and also cooler surface ocean, right?
During the ice age, it was a denser, yes, and a cooler, that's right, yeah. But also the cooling went quite far down as well, not just at the surface. Yeah. Yes?
I'm wondering if you're familiar with the paper by Lund et al. That came out a few years ago in Science, which looked at the flow of fresh water through the Florida Straits and suggests that actually the wind-driven circulation from the Gulf Stream northward actually was decreased in it. I'm not remembering my numbers exactly, but it is similar to the magnitude that.
Oh, really? Okay. No, I wasn't familiar with that paper. Interesting. Yes, Randall.
You may know that in recent years there's been a lot of discussion about second-year ice and first-year ice.
Right, yeah.
Would your models be able to add that as an attribute or an indicator?
In theory, because we do have a dynamic sea ice model in it, and yes, I think we could add it, but we didn't look at that. But the model does, no, hold on. Our thermodynamic model is, no, it's too simple, because our thermodynamic model is just one ice or no ice model, so a two-category ice. So to do that study, you'd have a multi-thermodynamic layer ice, so you could keep track of the different years of the ice, age of the ice. So we could not actually do that, yeah.
That would be an interesting check on
That's right, yeah. But no, it's very complicated right now, the age of the ice out there, and it really is, fairly young. So whereas in the old days, north of Greenland, that ice was there for years and years, and now after a year or two, it's quite mushy, and you don't get that multi-year, very solid ice anymore. Any questions from the back? There's some very studious-looking students back there. No questions? Did you understand what I was saying, more or less? Okay, good. Yes?
You used wind directions taken from sand dunes before in the time period before there were any historical records.
Do I do it?
Because anybody people do that.
People look at sand dunes. Probably. I mean, it sounds like a good idea. Yes, they do. I'm sure they do, yeah.
It's done for other time periods in the past. I don't know about for the Little Ice Age, though.
Certainly, wind records are implicit in very long records looking at Lus in China, for example, the amount of dust from the desert that accumulates during windy periods. And so that's used as a paleoclimate record in China for very long periods. Okay,
Well,
we'll wrap it up.
Dr. Mysak.
Okay, thank you very much again.